Okay, you're back from watching that video, and this is part two of classical conditioning. So, how is this learning, whether we're talking about Pavlov's example or even the example in the video with the roommate there being shot with the airsoft gun? So, a previously neutral stimulus, like the sound of a bell or the "that was easy" sound from the video, now evokes a response, right? It could be anticipation of food in Pavlov's example, or anxiety and flinching in the other example. But with repeated pairings of the CS and the UCS, eventually this sort of builds up so that the CS can eventually elicit the response on its own. So this learning phase, it often won't happen. There are some exceptions to that with like taste conditioning, where you can have one trial learning, but a lot of times it takes multiple pairings of the CS and the UCS before you'll have a detectable or even a strong response. And this is called acquisition. So what happens, or what you're looking at in this graph, is a lot of times it's plotted as, in this case, it's plotted as the amount of salivation, or a lot of times you could plot this as the probability of a conditioned response. And down here on the x-axis are the number of reinforced trials, and what they mean in classical conditioning is when the CS is followed by the UCS. So a pairing of the CS and the UCS. Then what you do is you test to see if there's a classically conditioned response by just presenting the CS by itself. And if it does, then you sort of mark that as being learned. And if it doesn't, then the response is not yet learned. So this acquisition, what you see is it takes a lot of times multiple pairings of the CS, UCS before you'll have a classically conditioned response. So this builds up. So you can have what's called an acquisition curve. And as you might imagine, the acquisition curves can change depending on the stimuli, depending on the organism. But a lot of them will rise like this, and then eventually they flatten out or plateau. That's called an asymptote. And a number of factors will affect this acquisition curve. Now, once we've learned this classically conditioned response, it's not the case that we always have to have this classically conditioned response. It can be unlearned. So just like we have learning, we can unlearn an association. Now, the way this happens is if you present the CS by itself. Right here in the slide, they're calling it unreinforced trials, but you present the CS by itself, not followed by the UCS. That would begin what's called extinction in classical conditioning. So the response is being extinguished or diminished or reduced, and you can see it over time. If you present just the CS over time, eventually the response will disappear. Now, there is something that's called spontaneous recovery. We're not going to dwell on this too much, but that's when a response sort of comes back even without additional pairings or associations. So we'll see something similar when we talk about operant conditioning. But the idea here is that we can learn and we can also sort of unlearn. Now you may remember, and we're going to talk about this in just a minute, classically conditioned fear with little Albert. And so the case is not that little Albert would always be afraid of white little fuzzy things. They could have him engage in extinction, and that's what they did to remove that classically conditioned fear response, or unlearn that classically conditioned fear response. And how do you do that? Well, you just present the CS by itself with no unconditioned stimulus, and eventually it will diminish. And this is actually used in cognitive behavioral treatment for phobias. So they can gradually sort of expose the person to whatever the fearful stimulus is to eventually reduce or extinguish that response. So I want to talk a little bit about, because a lot of times when you study classical conditioning, you don't really know like what's still relevant now. And so let me give you an example of how it's used and it's applied. So one thing that's being used is eye blink conditioning, and that's where you have a tone, like a sound. Sorry, the slide's a little blurry, but you have a tone followed by a puff of air to the eye, which is the unconditioned stimulus, right? So you have the tone, puff of air to the eye, and of course that will cause the person to blink, and eventually you learn when the tone happens that you blink. Now, why is this important? Well, some researchers have found sort of associations between the speed of acquisition, classical conditioning of eye blinking, and later developing dementia. So it could be a really early marker for developing dementia. Now, why is that important? Well, a lot of the treatments are trying to slow the progression. So the earlier that you can detect the disease, maybe the better the treatment will be for, or more effective the treatment will be for that particular disease. So the other example is, I mentioned it a second ago, is conditioned fear. So a lot of scientists, not necessarily studying in humans, but studying in animal models, if they're studying fear to develop drugs, to develop better treatment methods, they can create fear in the laboratory. How would you do that? Well, like with little Albert, you present them a neutral stimulus, pair it with, in this case, a loud noise, the unconditioned response, the unconditioned stimulus, and that creates fear, startle, in this case, the baby. And you pair that enough, and eventually the rat will take on, or the little white fuzzy thing will take on the fear-evoking response. And we can do this in the laboratory to create conditioned fear. You'll see some examples of this as the semester goes on, of creating conditioned fear in the laboratory. Now, one other relevant form of classical conditioning, because pretty much everybody has sort of experienced this, maybe we could talk about this in our class, but is conditioned taste aversion. So here's how it works. So an animal is exposed to some sort of novel food, like in this case, these granola bars. Then they receive an injection of lithium chloride. Now, lithium chloride will make these animals sick. Now, it doesn't kill them. It doesn't poison them. It's poison in the sense that it doesn't make them feel good. They don't feel good for about 24 hours or so, and then they recover, and then they feel fine. So you give one group an injection of this drug that makes them feel a little sick. Another drug gets a saline injection, which has no influence whatsoever on the nervous system. And then on day 2, you sort of give them exposure to the food and see how much of the food they actually eat, this novel food here. And as you can see over here, that if they're exposed to a drug that makes them feel ill, they kind of avoid the food. They don't really eat the food, hence the name conditioned taste aversion. So let's break down the stimuli in this. So the exposure to the food is the conditioned stimulus here. The unconditioned stimulus, and it can be confusing with like Pavlov, but this is the properties associated with the food, right? The taste and the smell, it could be, and the visual cues of the food, which we'll unpack here in just a second. But this is the conditioned stimulus. The unconditioned stimulus is whatever is making the animal sick, or in the control condition, there's no unconditioned stimulus, right? And then the conditioned response is sort of observing how much food they eat. A decrease in the amount of food eating is the conditioned response here. This is actually one of those, and I'll talk about this sort of at the end of our lecture 3. This is actually an example of where classical and opera conditioning kind of interact in a way. So just keep that in mind. It's not always clean. So just to recap this, so the conditioned stimulus here, food or drink. The unconditioned stimulus could be illness now. So if you have a taste aversion from something, a lot of times people eat some novel food, they happen to get sick, and when they get sick, they later then avoid that food. So you probably have a story. You could probably tell me about that story or reflect on it in your class discussion about taste conditioning, and I'll tell you about one of mine in particular. So then when you see that food or drink again, you don't feel sickness to the point that you did originally. If, like, say, for example, originally when you were poisoned, you were vomiting. You may not vomit here, but you will certainly feel nauseous. You'll feel a little sickness, and you'll want to avoid that particular food. That's what we're talking about for classical conditioning. And it's commonly believed or commonly talked about that the subject, so whether it's an animal or a person, is associating the taste of this food or drink with the illness. So they're associating taste with the illness. Now, my undergraduate mentor, Dr. Franchino, we called him Dr. F, he actually did some learning research. He's now long since retired. And he had a bit of work that he was doing with the Veterans Administration in a hospital nearby. And what he found, or what was reported to him, is like people undergoing chemotherapy treatment for cancer often get ill. And what was happening is they were avoiding food, which impaired, so they would lose weight, and it would impair their ability to heal, right? And this is just straight up taste conditioning, right? So you have whatever food or drink, you undergo chemotherapy, and now you don't really want to eat that food or drink. You undergo bouts of chemotherapy, and you're going to have lots of things that you're going to avoid, right? And the dietitians were carefully changing the tastes of the food for these patients in the hospital, but the patients still refused to eat, and they would report, it was the sight of the food that was sort of making them ill. So this got him thinking, and we wanted to study this in the laboratory. So we did study this in the laboratory. And this was the first published research that I was a part of as an undergraduate. And so what we were studying, we weren't studying people, we were studying chickens. Now, chickens have some advantages. We could rear them, we could hatch them, and we did have a hatchery, and we reared them, and we could control their environment, and they have a good sense of sight, but they don't have, and they have a good sense of taste, but they don't have a tremendous sense of smell. So we were able to isolate a couple of cues by using these subjects. What we did in the study is we, like I said, we hatched the chicks, and we reared them either on clear water or from hatching. Some chickens, to them, water was always red. We just colored it red with a little bit of food coloring, and it didn't have much of a taste or a smell associated with it. So for some chicks, clear water was water. For some chicks, water's always red, right? Then what we did is we did some taste conditioning. So on taste conditioning day, we changed the flavor of the water a little bit by adding a little bit of vinegar. Made it little, well, you know what vinegar is. Makes it a little tart, right? So tart or sour. And so we added a little bit of vinegar to the water. Now this, I should say, since I'm thinking about this study is very complicated. I'm just giving you sort of a brief overview. If you're really interested in the study, you can still go read it. There's a lot of layers to it. But I'm giving you sort of the upshot or important layers for the purposes of this class. So I'm giving you an abbreviated discussion. So anyway, we added vinegar to the water, and at the same time on test day, we were taste conditioning, so we gave them a lithium chloride injection following exposure or drinking of this vinegar water, and they would drink it. They didn't always drink as much of it as they would regular water, but they would drink it on this test day. But then we gave them a lithium chloride injection. Now, for half of the animals, this test solution was either the same color, so on what they were reared on, so clear water, same as clear water, or they got a novel colored water. So the water now is red. They go in test day and they're like, water's red. And they drink it and then get sick, which is what we're going to come back to in just a second. Or we reversed it. So the group down here is just to show you that there's nothing special about the food coloring. It's more about the interaction between rearing and the cues at work here. So the next thing we did is tested them. So after they were poisoned on that, the next thing we did was test them. So we tested them on different solutions. We split these groups in half again, and we tested them either on clear water or red water. Now on test day, no vinegar was added, so it's just water for them. And also I should say that we allowed the test days always happened well after the animals recovered. As I mentioned, a lithium chloride injection, for the chickens, usually a few hours, and they looked normal or behaved normal, but we would test them usually days later on these solutions. So the question I have for you is, what do you think happened? So let's break this down a little bit. Let's assume that you're a chicken, you're raised on clear water, you come in on test day, water looks the same, but it tastes funny, and you get a lithium chloride injection and you get sick. And then you're tested on clear water. What do you think you would do? Was it an isolated incident, or was there something special about that water? And as it turns out, for the clear water groups, they drank normally, right? Just a weird sort of experience with something that you always drink, and that one time it made you sick. But let's consider the group where they had clear water. They came in and it was this red solution. All of a sudden it's this Hawaiian punch, fruit colored stuff, and they drink it and it makes them sick. And then later they're exposed to it, and this is the first time they've had red water, right? Then they're exposed to it. What do you think happened? Well, they avoided this. They didn't drink normal amounts of this water. They avoided it. And by the way, the same thing is happening down here if you reverse all of the conditions. So what's the upshot of this? The key things I want you to take away from this. So taste conditioning effects first are reduced with previous exposure to taste and visual cues, right? So you're going to have the greatest taste aversion conditioning if it's a novel food, if it's the first time you've had it, right? Otherwise, you have multiple experiences. It's going to be harder to form that association. And probably what's happening here is you're habituating, right? You're habituating by eating foods that you always eat and they don't always make you sick. So novel visual cues produce stronger taste conditions. So it's not just the taste, but it's also the visual cues. That was really important. Visual cues were playing a role here. And in particular, what we found is they initiated whether the animal would actually approach and drink the solution. We had versions where they had the same tasting water, or it was same tasting, always tasted like water, or it had a novel flavor. And what happened is the visual cues would initiate whether the animal would even go up and sample it. So like if it's that red water and the first time that you saw the red water made you sick, you just avoid it by the sight of the visual cues. It's like the cancer patient saying, I can't look at that food. It's making me sick just to look at it. But after you taste it, the taste cues take over, right? So after you sample it, then the taste cues generally take over. So the dietitians were working hard to change the taste, but what they really needed to do was also change the visual presentation to help cancer patients not be repulsed by just sort of the look or the visual aspects of the food. So those are some examples of some things that are happening or relevant classical conditioning now, factors that affect classical conditioning. So one factor that affects classical conditioning is the contingency. And here what I mean is the probability that the CS is following the UCS. So you could have perfect contingency, so that means every time the CS appears, so does the UCS. Or you could have like half a probability, 50% of the time, the CS appears and is followed by the UCS. Obviously, this is fairly intuitive. You would have stronger, faster conditioning, right? Faster acquisition, stronger responding. If every time the CS appears, it's followed by the UCS. If you have a weaker relationship, you'll have weaker learning. Hopefully that's fairly straightforward to you, but that's contingency. Now, the other thing that we know is that the temporal relationship between the CS and the UCS is important. So we know this from looking at different kinds of conditioning. So I have them sort of overlaid for you here in graphical format. So trace conditioning, sometimes called delayed conditioning. What happens is, and this blue line here represents time. So the conditioned stimulus is turned on at some sort of time point, and then it goes off, and then there's a delay. Hence the name delay conditioning or trace conditioning. And then the UCS is turned on, and then it's turned off. And so what you can do is you can vary the time in between the CS and the UCS. So if you have a delay, shorter delays are better, right? So if the CS and the UCS are closer together, and in fact, they could even overlap in time, but as long as the CS comes on before the UCS, you'll have pretty strong conditioning. If you had a really long delay, we could manipulate the delay, right? We could have a few second delay, and we could have a several minute delay. As you might imagine, weaker conditioning with longer delays in between the CS and the UCS. Hopefully that's fairly obvious. The animal or the person is making an association between these two stimuli. It's harder to do if they're separated in time. Now, simultaneous conditioning is when the CS and the UCS come on at the same time. Now, as it turns out, this is very weak conditioning, very hard to produce conditioning with simultaneous conditioning. So what it's telling us, this particular type of conditioning is telling us, is that we need a delay. We need temporal separation. The CS has to come before the UCS at a short delay. Now, how do we know it has to come before the CS? Well, backward conditioning is when the UCS comes before the CS, and as you might imagine, there's no classical conditioning that really happens here either. So the reality is you need the conditioned stimulus to come before the UCS, at least by a second or some brief period of time before you'll have any sort of conditioning. In other words, the temporal relationship between these two stimuli is pretty important and affects classical conditioning. Now, all CS and UCS stimuli are not created equal. This is probably something you did not get when you talked about classical conditioning in your Psych 101 textbook. A lot of people don't realize this, but you can't just easily associate any kind of stimuli. One of the things that's really important is stimulus salience. And what I mean by this is how noticeable stimuli are. So the more noticeable a conditioned stimulus is, and the more noticeable an unconditioned stimulus is, the faster the learning you will have, right? If you had a really weak light, animals might not notice it. People might not notice it. And if it goes unnoticed, then it's going to be harder to form an association. Similarly, with an unconditioned stimulus, if you had a really, really weak unconditioned stimulus, say like a really, really weak shock where the animal barely felt it, then it's probably not going to elicit a very strong response, and not learning will be difficult to obtain. So the next one that we're going to talk about are logical associations, but I want you to read the Garcia and Colling paper first. This is a very difficult paper, so keep that in mind, but read that, respond to the reading reflection in Canvas, and then come back and watch part 3 of this video, where I will explain and break down this experiment so that you can understand it a little bit better, as well as finish out this lecture.